Hello everyone, this is our project presentation of computational geometry course assignment 2, where our job was to find the convex hull of a set of points. As we know, the convex hull is basically the smallest convex polygon which is enclosing a set of points S. Now, to make this convex hull, we have used the Jarvis March or the gift wrapping approach. In this approach, we have to choose an initial point and we have to compute the angles of all other points from this point. And based on that, we join this point with the point that has the lowest angle. And we continue this one by one so that we can find the complete outer covering of this set of points. So as we can see, this is our convex hull visualizer. This is our website. And to compute the convex hull, we can do it in two ways. First of all, I will show you the first way where we can generate points randomly. So let's say I click on generate random points and I enter any number of points which I want to generate. So I say that I want to generate 30 points. So this is a randomly selected set of 30 points that is there, and I just say compute convex hull. So now the convex hull of all of these points will be generated, and we can see the step-by-step simulation in this method. So we can see that it is finding angles to all other points and selecting the angle which will essentially form an outer covering, just like a rubber band is stretched across pins on a board. So the time complexity of this algorithm is O of n into h, where n is the number of points and h is the number of hull points. So we can see how this is working out, and we can see that now a convex hull will be computed like this. So we will see how this hull is being computed in real time. And after the hull is completed, we will also be able to see certain statistics like what will be the area of this hull, what is the perimeter, and the number of points that are being formed on this hull. So as we can see, the hull is almost getting completed, and yeah, this is how it is working. So it is again calculating the angle from all other points, and the hull is essentially computed. So after the hull is computed, we can see the area, perimeter, and other things related to the hull. We also allow the user another thing, like the user may select points on his or her own wherever he wants it. So that is also something that we allow the user to do. And let's say I compute the convex hull based on this. So again, it works in the same way, but this just gives the user flexibility to choose points where he or she wants it. Now, to make real world use cases of this, we have given the user two modes, which show two different real world use cases. First is the drone mapping. So what happens generally is that uh, there are a lot of terrains which we need to survey for, maybe the army needs to survey for enemy territory, or it's just security surveillance or anything like that. So what happens is we have a lot of locations on the terrain, and we have to the drone has to circumnavigate the outermost boundary. So it is essentially a problem of computing the convex hull. So again, in this terrain, I can just generate randomly any set of points. So let's say I generate 20 points this time, and after generating these points, so I generate 20 points, and after generating these points, I just say compute the convex hull. So after the convex hull is computed, the drone will essentially calculate all these points, and it will rotate the outermost boundary, surveying the enemy territory or whatever the use case is. And again, we can see all the statistics. But the most interesting feature of this project is the fishing mode. So a common problem that we encounter is that when fishermen go outside to catch fishes, uh, there are multiple fish species which are spread across the sea. So when we have to catch them, fishermen must find a lot of different varieties of species because different varieties command different prices. Therefore, it is essentially a problem of finding the convex hull of each cluster of the fishes. And by finding each cluster of the fishes, we can understand uh, uh, where exactly do we have to go to catch them. So, like, we can generate randomly any number of fishes. So let's say I generate 48 fishes, and then this animation shows how it's basically we have got three species of fishes. tuna, salmon, bass. And then the green color points are the fishermen. So these are the three varieties of fishes which are roaming entirely in the network, and there are convexal of all of these three. And in real time, we can see the overlaps in areas where there are multiple fishes and the areas where the fishermen must go so that they can find the maximum number of fishes. So the overlap between these convexals is very essential for finding the fish. And we again see all the important statistics that we want. And we have also given the user to uh, kind of make this if the fishes are going fast randomly and stuff like that. So user can do this through our convexal visualizer. Thank you.